just to sum up what you have been doing for the past 2 weeks, by the homework 0 and recitation 0, you should have somewhat of a good understanding of NumPy and basic Python functions. And then by the first 2 lectures, you were introduced to the concept of what a neural network is. You do not know how it's exactly trained, but you do know some of the major components that the neural network consists of. And then you discussed a little bit what a model is, and on like a very basic level, some algorithms that will be used for understanding how the training process happened. Right, and as for today's recitation, the plan is we would like to introduce you to deep learning frameworks that are used in Python, and specifically Pytorch. We're going to discuss how can you, like the different operations in Pytorch, how can you create a model, how can you train the model, and on a very on a very high level, we're going to talk a little bit about Backprop so that you can get a head start on your homework. Right, so the material for this recitation is up on the Git repository. There are 2 main notebooks there. One of them has different examples of the different operations you can perform using Pytorch, and the other is more of like a full end-to-end where it tells you how to build a network in Pytorch and how to train it. Right, like I said, today we're going to just have a small introduction on Backprop. It's not going to be in depth. It's not going to be in details, simply because on Monday's lecture, the professor will go over the details and the specifics of how Backprop works. But just for today, we're just going to have like a very like a high-level introduction on how it works and how can you use the different frameworks to actually train your model. Right, so deep learning frameworks, whether in Python or any other language, they give you some, or they provide you with some specific features, such as high-speed computations with matrix multiplications and arrays. That's why if you have access to a GPU, so the deep learning frameworks, they try to, if you have access to a GPU, they try to give you the opportunity to do parallel computations on those highly specialized entities that can help do matrix multiplications and matrix operations in general. And also, deep learning frameworks, of course, they provide tools for you to build any model that you want and train it, and of course have within the training backprop, because you need backpropagation to train your models. So to give examples of the different frameworks that are there in Python, there's Tensorflow, Pytorch, Keras, Theano, Cafes, although not used anymore, but still some people still use it. You see that there are a lot of different frameworks, and they differ by it depends on what kind of problem that you're tackling, the domain of your problem, basically, and whether you like more. Of course, their interface is different, their verbosity is different, their speed, their efficiency, and so on. So I'd like to give a small kind of introduction on the different frameworks that are used in Python, that are found in Python, one of which is Tensorflow. It's probably one of the most widely used framework out there. It's developed by Google, and it's extremely efficient if you know what you're doing. TensorFlow is one of the more harder, less intuitive frameworks out there, simply because, or at least one of the reasons that I think it's hard is because of its static framework nature. And by that I mean, before you actually train your model, you have to build a computational graph, and this computational graph stays fixed throughout the training process, right? So this means that when you build your network, you cannot change it afterwards. But again, if you do know how to use TensorFlow, it's extremely efficient. You can make your code highly optimized that it can just cut your training time by a lot, and that can save you like probably days in training if you're building a like a big scale model. Right, and then the famous Pytorch, the one that we keep telling you guys about. This is developed by Facebook. It's widely used, not as famous as TensorFlow, I'd say, or Keras, but still, it's very much used. It's very easy to use. It's very user-friendly, very verbose. Of course, there can be sometimes a little bit of a negative point because it means you have to explicitly say many things. So in order for you to train your model, you have to mention a lot of things for your network to start model. You have to explicitly say, for example, oh, right now I'm in training mode. Right now I'm in evaluation mode, and so on. Having said that, again, it's very easy to use. It's very easy to read. It's very easy to write. Of course, we encourage you to use this language. However, it's not necessary that you use it apart from Homework 2 Part 1. Homework 2 Part 1 is going to be in Pytorch, and you have to use Pytorch. But for any other homeworks or other parts of the homeworks, you can use whichever framework you're comfortable with. However, keep in mind that most of the TAs here are more comfortable using this framework, so we can help a lot faster and a lot more if you were to use that framework as compared to the others. Right. Another framework is Keras. Keras is a very high-level, easy-to-use as well framework. However, it does not give you, because it's super high-level, it does not give you some of the freedom that you can get when you use other frameworks such as Keras, such as Pytorch or TensorFlow. Of course, the performance of Keras is very much less as compared to Pytorch or TensorFlow. The simple reason behind that is Keras does not implement a backend to it. So this means that it's more like an interface kind of so it basically calls functions from other frameworks such as TensorFlow and Theano because those things are used as the backend and then they just run on that. Like I said, it's very much limited. I once tried to code a triplet loss with Keras. It was just a nightmare. I do not recommend that. Unless like it's a built-in function, it's really hard to have a lot of freedom with Keras. But again, like the comparison is if you want to build a simple model, you want to like publish it right now. It's very easy to use and it's very direct, I'd say. All right, and then the last framework that we're going to talk about today is called DyNet. It's a very specialized framework. It's used for language tasks, and it's developed by someone from CMU. Yay, CMU. All right. Okay, so now back to Pytorch, which is the important part. Like I said, if you have access to a GPU, Pytorch will automatically figure that out because it can figure out like the system's configuration, and then based on that can utilize whatever you have available. Of course, some laptops might have GPUs, some don't. So on AWS, you guys should have access to a GPU. You really do need an access to a GPU. You do not want to train on a CPU. Trust me, it will just take ages. On GPU, it's a lot faster. And the version of Pytorch that we recommend that you guys use is 0.4. It's one of the later versions. I think it's even the latest, if I'm not mistaken. Yeah, it's updated, less bugs, so on. Okay, so let's just talk a little bit about how data is represented in Pytorch. Just like NumPy, there are arrays in NumPy. There are these things that are called tensors in Pytorch. Those tensors are exactly like arrays. They are initially found on the CPU, unless explicitly said, and you can build whatever. You can build like different kinds of tensors, like float tensors, integers, 32-bit integers or 64-bit integers, and any kind of different ones to sorry, to create a tensor, you can, for example, float tensor, a random float tensor, you can just simply say torch the float tensor, and then you give it the shape of what your tensor wants to be, like what you want the tensor to be. And again, there are a lot of different functions like these. For example, you can initialize an empty tensor that takes less time simply because you're not changing the values within each input. You can have 0 and like all bunch of different things. And of course, you can change the type of tensors, just like AS type in NumPy. You can also convert between a NumPy array to a Pytorch tensor really easily. You can to convert from a NumPy array into a tensor, you just simply do this command. All right. So if you want to make it a float tensor, just put float tensor. If you want to make it an integer, put an int tensor, and so on. And vice versa, like I said, you can change the tensor into a NumPy array simply by doing this, .numpy. Yeah, and just like arrays, you can do operations between 2 different tensors or multiple different tensors. It's just simply like NumPy, right? So like if you want to sum over an axis, you can do that. If you want to exponentiate over an axis, you can also do that. You can do simple multiplications and summations, like element-wise operations. You can also do that without the need to convert it to NumPy and then back to tensor and all that. Don't do that. That's just it's a waste of time. And if you're doing this operation every single like on every single iteration, then it's just extremely time consuming, and you don't want to waste your training time on that. Right, and like I said, when you create a tensor, it's initially found on a CPU, on the CPU basically. And if you want to move it to the GPU so that you can perform the operations, the matrix operations on the GPU, you have to explicitly say, move this tensor from the CPU to the GPU simply by using this command, .cuda. And of course, if you do not have access to a GPU, if your machine does not have access to a GPU, then it will just pop up an error saying you do not have, like, I cannot move it because the GPU does not exist. But it will tell you, it will crash, it will tell you. Right, and just as a general information, if you have 2 different tensors that you'd like to perform an operation between them, you have to make sure that they are on the same processing unit. That is, if you have one on a GPU and one on a CPU and you want to add them up, you cannot do that. It will give you an error. You have to either have both of them on the CPU or both of them on the GPU. Now, saying that I would like to move something back from the GPU to the CPU, you just simply use this command, so .cpu on the tensor, and that will move it from the GPU to the CPU. And another kind of thing that Pytorch is doing is whenever you have a tensor on the GPU, you cannot convert it to NumPy directly. You have to first move it back to the CPU, then convert it to NumPy. You can still print it, you can still see what it is, but you cannot convert it to NumPy directly like that. Right. Okay. So enough of the frameworks. Let's talk about something that's a little bit more interesting, which is backprop. Like I said, you have not taken this yet. You will be taking this on Monday's lecture. However, I just wanna give you a small introduction on what backprop is and how does it basically work. Right. So from last lecture, you learned that gradient descent is an algorithm that can give you the local minimas and local maximas of a function, or tries to predict that, right? And the way it's yeah, so that's what it tries to do. And you've also learned that a neural network is like a function. It's like a universal function approximator, right? So you want to be able to predict those points. So based on, or not really based on, but very much similar to the ideas introduced in gradient descent, backprop is kind of uses the same ideas. So the way it works is there are two main steps to the backprop algorithm. The first step is the forward pass, and then the second step is the backward pass. Now, for the forward pass, what you try to do is that you try to compute the output and the output of the, after applying the activation function of each of the different layers, so that eventually you output the last vector, whichever it is, and then you perform a loss or a loss function over it. Of course, you've learned that for each of the layers they have associate weights with it and associate biases, and the way you basically do it is you just simply iterate over the different layers, and then in sequence, and then you multiply your input. So your input is a matrix here, if you think about it, because it's number of the batch size pair whatever the size of your input is, if it's a one-dimensional thing. You plug that through your network, you move over the different layers, and then you multiply this with a weight matrix. And this is the weight matrix of the layer, right? So you compute your z's and y's. So the z is just simply the multiplication of the weight with with your input to the layer, whether it's the input to directly the network or just in the middle, from a different layer to from for example layer I to layer I plus 1. And after you compute the z, you apply the activation function on it, because neural networks they try to utilize the nonlinearity concept, and this is utilized through the activation functions, right? So you apply the activation function on whatever the output of the weights times the input to the layer is, and you compute for each of those layers. You compute the outputs and the outputs after activation. You do this why? Because you want to eventually reach the output vector of the entire model, so that you can perform a lot, so that you can compare it to your targets, and then based on your specifications of your loss function, you can then know how much loss you have. And how much divergence is there between the target and the output of your model. And based on that, you will do a backward pass based on the loss that you compute. You're going to do a backward pass on the model that then that can then later change and update the weights and the biases in the correct form, so that you can so that you minimize as much as possible the loss or the divergence between the output of your model and your targets, right? So just like in gradient descent, you do the derivation, and that's basically what the backward pass is trying to do. So after you computed everything, you go from the last layer all the way to the first layer, computing the divergence with respect to different vectors. The output of the layers and the output after the activation, and after you compute these guys, the divergence with respect to y's and z's, then you can just update your weights with respect to a specific function that's given. And of course, like I said, this is not a very explicit and very a big introduction of backprop, because the professor is going to definitely go over all these, and this will make sense. I know it looks like a lot of math, but it does make a lot of sense, and the professor will go over in details on Monday's lecture. Right. All right. So like I said, some at the beginning, some frameworks, they give you backpropagation, so they already implement backpropagation for you. You do not have to explicitly implement that. However, in your homework part 1, you actually have to implement backprop from scratch, right? So that's the task of that part of the homework. But in Pytorch, there's a command that basically does the backpropagation for you, and it's called backward, right? Now the key point here to get from this slide is when you create a tensor, right? You have to explicitly say to Pytorch that, look, I am going to perform at some point a backward pass on this. I'm going to perform backpropagation. So make sure you remember that, or you remember the gradients, or when we perform that. So you remember how many operations you performed on this, so that you can do the derivative on that tensor eventually, and you can capture those points. And to tell Pytorch that this tensor is going to be part of a backpropagation, or I'm going to backpropagate on it eventually, is you use require _ grad equals true. Because normally that flag is set to false simply because, you know, when you use normal tensors, you're just using normal arrays. There's nothing special about them. However, if you want to, like I said, if you want to perform a backward pass, you have to explicitly say, look, this is a special tensor. Make sure that you remember what I do to it, so that you can derive eventually, so that when I do the backward pass, you know how to derive it. So if you let's go over this example a little bit. So here we created x, which is a tensor that goes from 0 to 3, right? Inclusive on both sides. And then z is defined as this, b is defined as that, and y is equivalent to this. Right. So if you see here, we performed a backward on y, right? So the way, but because of y is consistent of the different tensors, when you do backprop, you are going to get d of y with respect to d of z. For example, let's take z for example, and this value is captured within the gradient in that tensor. So again, just to clarify a little bit more on this, so if y is equivalent to is made of many tensors, to get the gradient of the tensors that are consistent inside y, you basically do z.grad, right? So if we look at this example, we see that if we look at print x.grad over here, which is 1, 11, 21, 31. The reason why it came out like that, because z here is x squared, right? So we can rewrite y to become 5 times x squared plus x plus b, right? Now let's derive y with respect to x. So you're going to end up with 10x plus 1, right? And whatever x was, which is 0, 1, 2, and 3, you basically perform on x 10x plus 1, right? And that gives you 1, 11, 21, and 31. So does this number make sense? Okay, cool. And by the same concept, you perform this on b, right? And y is equivalent to 5 times x squared plus x plus b. And if you derive that with respect to b, you should end up with 1, right? So that's why you end up with only 1s. And here for z, because z is not really a special tensor, it's just basically x squared, that's why you have none. Yeah? All right. And just as a something that they implemented in Pytorch, when you perform a backward, they do not erase, or they do not forget whatever you've already performed before. So this means if you were to do two consecutive backwards, you see that the values are not they're not being reset back to 0. So normally what you should expect, if you were intuitively, what you should expect is when you perform the first backward and the second backward, they should output the same thing, right? Because you're doing the same exact operation. However, you see that they're not doing that. And the reason behind that is that Pytorch accumulates, basically accumulates the different gradients, right? Why is this helpful? This is helpful because sometimes if you want to, for example, if you want to create a big batch size, but you just can't simply because your GPU cannot take more data, instead of just replacing it with 0, you can just keep on accumulating up until you reach your desired batch size, and then, yeah. Sure.
How does accumulation work? Does it just sum it up?
Yes. Yes. And of course, like I said, if you want to reset them, you have to explicitly say, make it zeros, right? I think that there's another command that you can use, but that's for later. I think you'll see it later. That can explicitly reset the gradients of your optimizers or and so on. So yeah. Sure.
Because backward prefers to apply to just one tensor. You can do it with y.backward, but then you have to pass as an argument of backward the coefficients of the gradients of each dimension, which is boring, so you just do sum.backward.
What do you mean when you say y.sum?
Y.sum is just going to take the sum of all the elements of y. And then on this sum, you can apply backward, which is basically the same, but a little bit easier than calling backward directly on y, which is multi-dimensional.
Alrighty.
Good moment to take a look. Thank you, Sheldon. Do you have any other questions, by the way?
So if we don't add the sum particle of the result. Sorry? If we just write y and backward, then what the will be the result?
If you just write y dot backward and y is like this, y dot backward parenthesis would not work actually because it needs an extra argument. Basically, you'd have to give it a vector of 1, 1, 1, 1 to say, okay, I just want to put the one gradient of the first element and the gradient of the second element. And I can give you the reason why it's done this way, but just the simplest way to compute the gradient is just to take the sum and do backward. Anything else? Yeah.
Why does the graph give none as an answer?
Because, good question, because the backward will compute the gradients of everything, but it will not retain the gradients of everything. It only retains the gradients of what you can call the leaves of the graph, which is not all the variables, but not the intermediate computational variables. Which kind of makes sense because, like, you can consider, for example, B here. It's like you can consider it a parameter of your network, and Z it's the output of the layer, and then you add B, and you get your final output. But you're not really interested in the gradient of Z. You're interested in the gradients of your actual variables, but not of the intermediate computations. So Pytorch just forgets this one as soon as it computed it, except if you ask it not to do it. But that's for something else that's not very useful. It will make much more sense when we see how you do backward on actual neural networks and how it works with parameters and everything. So I'll just quickly here at that moment. By the way, since we are questions, English is not my first language, so if you can't understand something I say because of the way I pronounce a word, please tell me. I won't be offended. Okay, so now you know tensors, backpropagation. Let's see how you do a neural net. So you know from the course that a neural net is basically... Oh, good idea. Where's the mic? Is it fine this way? So in the most abstract way, a neural network is a very big function depending on a lot of parameters, and you give it an input and it gives you an output in the simplest way possible. So in Pytorch, it's the same. The definition of a network in Pytorch, it's basically an element of the torch.nn.module class. Module is just neural net. So this is an abstract class, if I'm not mistaken, which means you cannot instantiate an element of this class. So what you do is every kind of neural net is actually a subclass that inherits nn.module. So you have you can create your own, or you can use the ones that are directly in Pytorch, that are the simple ones. For example, the one you all know about, the single layer perceptron, it's torch.nn.linear. That's just the simplest network you can get. So you have inside of this you have a weight matrix and a bias vector, and it takes a 4-dimensional input and connects it to a 2-dimensional output, and that's all. So how do you call it, and where are the parameters in this? So for every element of nn.module, you'll have a forward method, which calls applies the network to an output that you give. And a little way to do a little bit faster is to directly call the network. That works. You just net parenthesis input parenthesis. It's exactly the same. And you can see here, if you create some input, you get a 2-dimensional output as expected. When you create a network, the parameters are randomly initialized, so there is no particular reason to why you get this output. It just depends on the parameters. And by the way, the parameters, you can access them with the parameters method. So this is something I'm being a little bit thorough about how these classes work and explain some things that are not always useful in Pytorch when you code. I think it's super important that you understand all this, for example, so that you can understand when Pytorch gives you an error message or something. It will make things much easier. So as you see, if I call net.parameters and I see, and it's sort of a list where you can iter and print your different parameters. So as you see, you have one 4-2 matrix and one 2-dimensional vector, which corresponds to the weight matrix and the bias vector. And you see they're of type parameter. Parameter is actually something that encapsulates a tensor and works pretty much the same way as a tensor, with a few minor differences that are actually important. One of them is that parameters always have require grad equals true, so that you can compute their gradients, which is the point of training, and others that we'll see right after. This is for a single layer perceptron, but that's not what you want to do usually. For example, let's say you want to do a multi-layer perceptron. How would you do that? So you can write your own version of the module class, give all the parameters and say what they do and define everything. I recommend that you never do that. That's how it looks. So you see I defined several matrices, several vectors of all of type parameter, and in the forward method that I overwrite, I explain that you use the first weight and bias for the output of the first layer. Then I define, I use max with 0 to define the rectified linear unit activation. And I do the second layer and I return the output. That's a lot of words and it's not clear. You have to pay attention to how you multiply matrices. Basically, you never do that. I did it mostly because for two reasons. Sometimes you won't have the choice because there's something you want to do that no default class of Pytorch can do for you. The other reason is that I want to show something that's super important, which is that as you can, all my attributes in the class are of type parameter. And the result of that is that if I call all these attributes will be added to the parameters list of the network. So if I call dot parameters on this network, it's going to return all my weights and biases automatically. And that's how Pytorch works. And that's kind of important. You'll see later why. But if you don't want to do that, how do you do it? You can do it this way. So in Pytorch, the networks, there are actually bricks that you can reuse in bigger networks. So linear, the single perceptron, you use it as a layer. So I define layer 1, I define layer 2, which is actually just the activation of layer 1, and layer 3, which is the second linear layer. And I call, in the forward method, I apply these layers successively, and return the final output. And what's awesome is that all the parameters of my sublayers will become parameters of the big network. To recap, the attributes of your class, they can be of type parameter or they can be of type module. It works too. Now, this was still a little bit verbose because as you see, I defined several layers successively and then I just apply all of them. So fortunately, there is a little shortcut to do faster than that. You can just define an nn.sequential element this time. You don't write a new class, you just call an instance of this one, and it's going to return a new module. So sequential just means it's a feed-forward network that first apply the second thing the first thing you give, then the second one, then the third one, etc., etc. All clear? So all of the things I did for now will do exactly the same thing, but this one is the best because it's shorter. But this one you won't be able to use every time, only in the simple cases. But for example, in homework 1, part 2, that should be enough, I think. Now, I did 2-layer perceptrons until now. If you want to do more, you can combine your networks between them. You can do a lot of fun stuff. I won't focus too much on that. Like here, for example, as you see, I make big list of layers of the size of a list I give, and I return a sequential of this big list, and that gives me a multilinear perceptron with ReLU activations that I can then combine with other stuff if I want. So you can have the tree structure of your classes, and you can use that to write as little code as you can. So what do you do at the end of a network? You know that from the course that in training, what you want to do is have a differentiable divergence between your output and the desired output, and use that to compute the gradients of all the parameters. So the divergence, we tend to call that a loss in machine learning. You'll see that in more details next week, but this is the cross-entropy loss, which is super useful in multi-class classification. So the idea is I have like several classes, like in the MNIST dataset with digits, and I create, for example, if I have 10 classes, I create a 10-dimensional output. Then I apply a softmax. Which is you take the exponential of every element and you normalize. And then the divergence is comparing the softmax with the one-hot representation of your results. So a vector where the right class has a 1 and all the others have a 0. So if you this sum is actually all the terms are 0 except for the good one, which is minus log of the result in this. So you can see that the closer this is, like the biggest, the closer this y correct y was to 1, and the smallest the divergence is, which is what you want.
So just say, since you're using one hot desired output, are you using these state or categorical or all kinds of attributes?
Is it cross entropy loss?
Yeah, it's in. I guess it's categorical. Yeah.
Yeah.
You.
You'll have mean squared error for.
Sorry.
You'll have mean squared error for the normal data, right? The loss function should be mean squared.
You could use this square error for regression, for example. By the way, the different losses and their application cases will be seen in much more detail in the next recitation. I just took this one, which is actually, for, you can call it categorical attributes. You'd say categorical more if it's an input variable. Here I'm considering the output, so I'd say it works in the case of multi-class classification. You just have n classes and you want to find the right one. So the losses are defined also in Pytorch. So for cross-entropy loss, which you will use in almost all homeworks, you'd use torch.nn cross-entropy loss, which will actually, you don't do a softmax before that. The softmax is included in it. And it's actually, it tends not to do a softmax, but a log softmax, so that you avoid some stability problem in the computations. So you take the output of your final linear layer and you feed it to cross entropy loss, and that gives you your divergence. So this is how you use it pretty much. Note that here, instead of feeding a vector to my network, I gave like a two-dimensional tensor, which is what you call a batch. So it's like three inputs concatenated that I can feed at the same time. That makes computation much easier. Then again, this will be clearer after the next lectures. I just mentioned you can feed one-dimensional output or two-dimensional output to your networks. It will work either way. But in practice, you always feed it batches. So now that you have that, you can compute your divergence, but you haven't actually trained your network. So you need to apply gradient descent or something else. But the something else, it's for next lectures. So we just do gradient descent for now, which is the one that was mentioned by the professor 2 days ago. So to do that, you need an optimizer, which is kind of like module. It's supposed to be a class that inherits torch.optim.optimizer, which explains how this class is supposed to work. So for gradient descent, we just use the simplest one, torch.optim.sgd, which stands for stochastic gradient descent, which is a little bit different than gradient descent, but if I use it correctly, it just does exactly the same. So that's how you initialize an optimizer. You call the class, and as argument, you send first all the parameters that you want to optimize. So here, what I want to optimize is my network parameters. So I just call net.parameters and send that. And you can send a ton of additional arguments that specify how your optimizer works. The most important one being LR, which means learning rate, which defines by how much you modify the parameters at each step. So that's what you multiply the gradient with to define by the modification of each parameter. So that's to initialize the optimizer. If you want to call it, you just do optimizer.step, assuming that you did backward before, so that all the gradients are already there and you're just asking to do the optimization step. So if you try to do it like several times for several iterations of gradient descent, it would look like this. So here I do 100 iterations, and note that, like Shayden said, if you just repeat operation, it's gonna accumulate gradients and never put them back to 0. And if you did that, you'd use kind of the same, you'd reuse the same gradients several times in addition to the new ones, which would be, it is hardly ever what you want to do. So you just, at the beginning of your iteration, you just call optimizer.zeroGrad, which is the second and better way to put all the gradients to 0. Gradients of all the parameters that you give the optimizer. So you compute the output, you compute the loss compared to the desired output, you call loss.backward, and then you do optimizer.step. And, well, that's pretty much all we want to cover. So we can move on an example. You all have access to the Pytorch example notebook. And hopefully you can call that in an environment that has Pytorch. Okay. That works. So this is just an example for the class. It has not much point except explaining all this. So the example is based on what you saw in the first week, where we were talking about universal networks as a universal classifier. So you saw that you can pretty much approximate every kind of boundary on your space. So here as a boundary, I chose a circle. It's a bit distorted because of matplotlib, but whatever. Yeah. You can access this by from the GitHub repository of the class. We're in the Recitation 2 folder. Do you have that?
Yeah, I'm only seeing tutorial Pytorch, tutorial NumPy, and then Pytorch example, but it's not coming up as this type of notebook. It's coming up as a Python.
Really? Oh, this is bad. Let me check. Let me check. Okay. Yeah, you need to, if you have an environment on your computer, a Python environment. If you clone this GitHub repository so on your computer, and you can, and you have Jupyter on your environment, then you just call Jupyter Notebook and you open this from Jupyter. Is it? Okay. Do most people have access to it this way? Okay, so we'll try to approximate a circular boundary. So you cannot do perceptron. MLP could not approximate that compute that exactly, but you can approximate it with a lot of polygonal figures. So we'll keep it small, and we'll try to approximate it, for example, with a hexagon. So this is code to generate, first I import the libraries. This is code to generate points. So I generate it basically half points inside the circle, half points outside in my data set. So to do that, I sample uniformly, but by using the polar coordinates. But that's really not important. What's important is that in the end you have a tensors train X, train Y, validation X, validation Y, test X, test Y. So I'll train on this set and look at the results on other ones. So I have 10,000 points in the first one, 500 points in all the other ones. So basically what you would want to do theoretically is something like this, but you know that when you saw that, it was when you had thresholds as activations. Here you will have like radio activations, so it's not exactly the same, but it should work in a close way. That's what the image you should have in head. So like in the slides, here's a function that will generate for me a neural net of the number of hidden with the 2 layers and the number of hidden neurons that I want in the first layer. So if for example, if I want to have a hexagonal boundary, it makes sense to call it with 6 hidden neurons. So it looks. So I transform all my datasets to tensors because they were NumPy arrays initially. And here's the training routine. So every time I want to train, I send my network, I send the dataset. The dataset contains training and validation data. And I also send a flag, GPU, that is a Boolean telling me, do you want to compute this on the GPU or not? That's a good way to organize your code because you never know when you will have access to a GPU or not. So by using something like this, you can just transform one thing to true from true to false and change it. So the criterion, which just means the loss, the optimizer will be SGD with my parameters. If I call GPU, I transform everything to CUDA tensors, including the network. I don't know if we mentioned that before, but if you want to, as we said, GPU tensors can only work with other GPU tensors. So if you want to compute everything on the GPU, you need your parameter weights and biases to also be on the GPU. So you need to call for that net equals net.CUDA. So in an iteration, what do? I compute my output by calling net train data. I compute my loss. I do loss.backward. I compute my step, and I zero all the gradients. And that's all. So once in a while, in the iterations, I call the network on the train data and also the validation data, and I print my loss and my accuracy for each of them so that I can see what progress is made. You can call these functions yourself. I'm not going to do it because the training takes a few seconds and I'm not going to lose time. So the data set is defined as this. If I call on the model I initialized previously, I call the routine. It does something like this on the CPU. So you can see the training loss that starts high and is gonna decrease and decrease, and at the same time the accuracy, which at first is 0.5 because it's random, is gonna get closer and closer to 1. So we're at a lot of iterations. Training loss is now at 0.2. Accuracy 0.95. You see it gets very high very easily because a circle in the two-dimensional plan is something super simple. In practice, this is for a network that small, it's honestly pretty good. And in the end, I get accuracy of around 96. So you knew that you could not obtain an exact circle, so there was pretty much no hope of getting accuracy bigger than equal to 1, unless you're extremely lucky in the way your dataset was sampled. So that's with 6 neurons, and if I try with like 3 hidden neurons, so that way you could expect it to approximate with a triangle or something. Then, see, it's not super obvious from the data, but it's the accuracy is a little bit lower. I could have expected that it would be more like 0.9 than 0.94, but whatever. So later than that, I define functions to print the result of the model on the test set to see what it does. I'm not focusing too much on this function. Just look at the result. So you can these are the points that have been classified in the circle, and these are the points out. So it pretty much works. You can, from the look of this, guess what kind of where the linear boundaries kind of are. So if you count, you can see that I think it's probably actually a hexagon, which is good. But more surprising, the one that you expect to be a triangle is actually a square. So that's because since you can use the final neuron for something different than just an end on what's before. It's actually that's called what you call the distributed representation, sort of. The idea is that it doesn't work like it's just threshold activation, but all the neurons are working for the classification. And depending on the training you have, you could have a square, you could have a triangle, or you could maybe the training will fail and fall into local minima, and you'll just get two lines. It can happen too. So I recommend that you compute all of this several times and print every time and see the differences between all the times you try to train, and see that it does not actually does the same every time, except for the first one, because it's bigger, so it has much better chance to go where you want it to go. It's not a general rule, but here it will work. If I try with just 2 neurons, see that here I'm gonna get 2 boundaries, like you would expect. So it's a very bad approximation of a circle, and you'll see that the accuracy this time is much lower than it used to be. So that's pretty much it for this example. I don't know if some people tried to launch it right now and had an issue. If not, you can launch it later and ask about it on Piazza or whatever. Let's go back to the slides. So just to finish the recitation, I want your attention to focus on a few issues that are going to happen all the time. So if you see them once, maybe you'll remind that when you write some code, and it will help you debug it. So there are the ones that we already mentioned. For example, when you try to do an operation with a tensor, a CPU tensor and a GPU tensor, it's gonna fail every time. The ones that are you're bound to have are when you make an error in the dimensions of matrices you try to multiply or something like that. Same as NumPy. Probably already saw that in homework 0. Well, it's the same in Pytorch. Is it working? Yeah. Interesting one. If you use the multiply symbol It's an element-wise multiplication. It's not a matrix multiplication, so pay attention to that. You can see here the difference between two results. Another one that is bound to happen, view is the equivalent, Pytorch equivalent of reshape in NumPy. So sometimes you want to make your, for example, you have a 3-2 shaped tensor, you want to make it a 2-3 shaped tensor. Pay a lot of attention whether you want to transpose or not, because it's not at all the same. You see, if you call view, it just values keep the same order, they just reorganized, so to speak. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Transposition is different. So that's all for that one. Broadcasting is pretty much related to dimension errors. Broadcasting is that you can sometimes add a tensor to another tensor even if they're not the same size, or if they don't have the same number of dimensions. Because, for example, in a matrix, if you try to add something of the shape of a line of the matrix, it's going to add it to every line, because Pytorch tries to guess what you want it to do, like NumPy. But if you try that with a column, it's not going to work. So you can try to. Here you see I made. If I try to add something of the shape of one line of X, it works. If I try something of the shape of one column, it won't work. But if I reshape it so that it's of dimension, yeah. Sorry, zoom. I hope I can do that. No. Is it better or is it the same? All right. So I'm not going to focus too much on broadcasting, but you'll get an error that looks like that, so learn to recognize them and try to look for your errors. Okay. GPU memory error, that's when you have a too big network and you feed it with a too big batch of vectors, and you'll get, oh, it's not written. Yeah, I hoped you could have the CUDA, you'll have CUDA out of memory. That's what will be written. And in that case, you were a little bit too ambitious, so either you make a new AWS instance with more GPU, or you reduce your network, or you take smaller batches. And it's going to be slower. Okay, this one